Recently in class, we've talked about the dot product of two vectors. If u and v are vectors, the dot product of u and v, which we denote with a large bullet, we don't want to confuse this with multiplication, is the magnitude of u times the magnitude of v times the cosine of the angle between u and v. And a classic example in physics is if u is force and v is displacement, then the dot product represents work. Now the dot product has several important properties that we've discussed. It only makes sense to compute the dot product of two vectors, and the result of the dot product is a number, or a scalar. If the dot product of u and v is 0, that means theta has to be 90 degrees, or pi over 2, so the vectors u and v are orthogonal, which is to say that they are perpendicular. Now, in general, this formula requires that we know what the angle between u and v is, and we usually don't know that. So typically, we compute the dot product using the component forms of u and v. So if u is this vector and if v is that vector, then we multiply the corresponding components and add. So u dot v in this case would be 1 times 2 plus 2 times negative 4 plus 3 times 7, and that results in a number of 15. Now the cross product is another way of combining two vectors in a product of sorts. So the cross product, u, and we put a cross symbol, v, is the magnitude of u times the magnitude of v times the sine of theta times n, where n is a unit vector perpendicular to both u and v and whose direction is determined using what's known as the right-hand rule. Now, we'll explain in more detail what that means, but let's just compare the formula. So the magnitude of u, the magnitude of v, we saw that in the dot product formula. Now we have the sine of theta, whereas we had the cosine of theta, but now here we have an extra thing added on. We have a vector. So the cross product is going to be a vector. This whole thing out in front is a number, and then we're going to multiply it by this unit vector, n. Let's take a look at an example. Let's suppose that u is the vector 0, 2, 0, v is the vector 0, 0, 3. So with my wonderful graph here, the vector u points out 2 units along the y-axis. The vector v points 3 units up the z-axis. The length of u is 2, and the length of u is 2, the length of, v is 3. And we know the angle separating u and v is pi over 2, or 90 degrees. Now, there are 2 unit vectors that are perpendicular to u and v. One would be the vector 1, 0, 0, which points right out of the page straight at you. The other one would be minus 1, 0, 0, the vector of length 1 that points back into the page. Now, which of those two do we use for our n? We use the one obtained using the right-hand rule. Okay, now here's what that means. Take the heel of your hand, put the heel of your hand at the origin, or where the two vectors are, where their tips, where their tails coincide. And then put your pinky down at the end of the first vector, which is u in this case. So I use the heel of my hand and I use my pinky, and if I put that hand down like that, wrap your hand over to the vector v like this. Your thumb has to point in the direction of the desired unit vector n. So let me say that again. Put the heel of your hand down at the tails of where the tails of the vectors coincide. Remember, we can move vectors around without changing length and direction. Put the pinky of your right hand at the end of the first vector and cross your hand so it ends up on the second vector, which is v in this case. And if you do that, your right hand, the thumb, has to point in the direction of the desired vector n. Now, of course, if I switch the order of this, if I took v cross u, I'd have to somehow contort my hand so that the heel started at the origin and my pinky ended up at the the tip of V. So it's important that we consider the directions. We consider the order, U cross V, as opposed to V cross U. So in this case, the unit vector obtained using the right-hand rule of the two possible choices would be the one coming out of the page, 1, 0, 0. So what we have is that the cross product of U and V is the magnitude of U times the magnitude of V times the sine of theta times this unit vector n. Magnitude of U is 2, magnitude of V is 3, the sine of theta is 1 in this case because theta is pi over 2, and then n was 1, 0, 0. So what we end up getting is 6, 0, 0 as the cross product. So that's going to be a vector of length 6 coming out of the paper towards you. Let's take a look at a slightly different example. So suppose the vector U now is 0, 4, 4. V remains the same as 0, 0, 0, 3. Now, if I draw the vector U in this case, it's going to end at the point 0, 4, 4, which is up here. So now we have that vector. So if this is the vector U, this now is in the zy plane, the angle that separates the two vectors is going to be pi over 4 radians. The length of U, if this is the vector U, the length is 4 root 2, and the angle separating U and V is pi over 4, but n remains the same because n is just, V is just pointing up in the zy plane, V is pointed straight up, so if I use the right-hand rule, putting my heel at the origin and my pinky along the vector ending at V, the right-hand rule dictates that the vector would still come straight out of the paper. Hopefully that will focus here. Okay. So in this case, the cross product would be the magnitude of U times the magnitude of V, 4 root 2 times 3 times 1 over root 2, because that's the sine of pi over 4, and this would simplify to be 12, 0, 0. Now these were very special cases where the vectors were perpendicular, and they were nice vectors in the sense that they were just along the coordinate axes. Let's talk about a more general formula. Usually it isn't this easy. So we want to find a component-wise formula. If we know the components of U and the components of V, how do we do it? Well, here's a formula that you can find in several textbooks. It's a little bit messy. We take the second component of U times the third component of V, subtract the third component of U times the second component of V, and so on and so forth. It's a messy formula, and frankly, I never have it memorized. We can expand this using what's known as a determinant. So what I've done here is I've put DET for determinant across the top row of my matrix. I put the unit vectors I, j, and k. They go in the x, y, z directions respectively. In the second row, I put the entries of U, and in the third row, I put the entries of V. And it's important that we do this in the correct order. Were this V cross U instead of U cross V, the two rows would be interchanged. Let's take a look at a particular example. U is 1, 2, 3. V is 4, negative 1, negative 2. So let's take that previous example. Now we're going to use what's known as cofactor expansion. So here's the idea of cofactor expansion. The first thing we're going to do is we're going to expand along the top row. So I'm going to cover up the top row and the first column of my matrix. And then I'm going to compute what's known as the determinant of this 2 by 2 submatrix. I take the product of the diagonals, which is minus 4 minus the product of these are what we call the back diagonals. So I'll have 2 times negative 2, which is minus 4, and I'll subtract negative 3, which gives me negative 1. So minus 4 minus a minus 3 is negative 1. Then we move over to the j column. we cover up the row and the column containing the j. You'll notice that we have a 2 by 2 submatrix consisting of 1, 3, 4, -2. We repeat the process. We take 1 times -2, which is -2, subtract the product of these two, which is going to be -2 minus 12, which is minus 14. And then we move over to the row and the column containing k, and we do the same thing. 1 times -1 is -1, minus 4 times 2, which is 8. 1 minus 8, -1 minus 8 is -9. So that's how we get the cofactor expansion. But there's one little twist, and that is when we looked at the j column, the j row and column, we put a minus sign here, not a plus sign. And that's just a convention. And the reason is that the j falls in row 1, column 2, and 1 plus 2 is an odd number. You just need to remember that when you expand, you need to add a minus sign there. So this all simplified to be -1. We have minus j times a minus 14, and we have plus k times this minus 9 here. So I have minus I plus 14j minus 9k. And if I write that in my usual angle bracket notation, it's -1, 14, minus 9. Now I should point out that the cross product using this method is still quite tedious, and I'll leave it to you perhaps to learn how to compute the cross product of two vectors on Mathematica, or Wolfram Alpha will do it quite easily as well. So here are some important properties of the cross product. It only makes sense to compute the cross product of two vectors, and the cross product of two vectors results in a vector. So let's take a look at this example. U cross V is a vector. W is a vector. Can we take the cross product of two vectors? Yes, and the result is a vector. Now take a look at this example. U cross V, that's a vector. W is a vector. Can we take the dot product of a vector with a vector? Yes, we can, and the result is a number or a scalar. Now, U dot V, that's a number. Can we take the cross product of a number with a vector? No. So this quantity is nonsense. Let's take a look at this. U dot V, and then this quantity is multiplied by W. Now U dot V is a number. So we're taking a number and we're simply multiplying it by W, which is going to stretch it or shrink it. So this will be a vector. Another example, U dot V, result dotted with W. This U dot V is a number. We cannot take the dot product of a number with a vector. We can only take the dot product of a vector with another vector. So this is nonsense as well. If U and V are vectors, then the cross product U cross V is always perpendicular to both U and V individually. That's because of how we use the right-hand rule. This cross product is anticommutative. That means that if we switch the order in which we take the cross product, it's minus the cross product U cross V. So the difference, if we switch the order of the vectors, the difference is in the resulting direction. The cross product of two vectors is the zero vector provided U and V are parallel to one another. And here's the reason for that. Go back and look at this formula. If the vectors are parallel, the angle between them is going to be 0, and the sign of 0 is 0. So that means the cross product would be the 0 vector. Not 0, but the 0 vector, because the cross product of two vectors is a vector. Just like the dot product, the cross product is bilinear. What that means is that if we stretch U and then we take its cross product with V, we can simply take the cross product of U and V and stretch the result by a scalar C. Similarly, if we stretch V by the scalar C, take the cross product of that with U, we can factor out the C as well. These are both very convenient rules. So here are some problems for you to do in preparation for class. Suppose U is U is the vector, see if we can get this in focus. U is the vector, this is a 3, negative 4, 2. V is the vector, negative 1, 2, 5. Calculate the vector U cross V using the expansion method that I showed you on the previous page, or the formula that I showed you even before that, the one that I can never memorize myself. Suppose U and V are general vectors, not necessarily the ones in the preceding question, and suppose that the cross product of the two is 2, 3, negative 1. Calculate each of the following. Use properties of the cross product. V cross U, 2U cross 3V, U cross V cross U. So see if you can do these in preparation for class.